Hello, ladies and gentlemen, and welcome back. Thanks for joining me. We're looking at question number 9. It's 9 on the 2004 Euclid. A Kirk triplet is a triple XYZ of integers, such that, okay, we got a list of conditions here. X is greater than Z. That makes sense in our picture. Z is a prime number. And there is a triangle. Okay, this is where the picture comes in. There's a triangle ABC with AB equals AC equals X. BC is Y. Okay, so we got an isosceles triangle, a Y, and there's a point where this length is Z and this angle is 60. That means this angle is 120. Oh, okay, but those are the only 3 conditions. I'm curious about the prime number. You don't usually see prime numbers and geometry together. They don't mix a whole lot, in my experience, because you usually get a prime number when you're doing some sort of factoring, where, and at some point we might need something like Z divides into this, and then that might break something up. Yeah, it's usually what I think of with prime numbers, and yet with geometry we don't. I mean, algebra is really where you're doing division stuff. So this is interesting. This is probably going to saddle a couple of mathematical techniques here, or maybe there's more than one way to approach something. I don't know. But let's get back to it. A. Find the Kirk triplet with x equals 7 and z equals 5. Okay. So the only thing we're missing is y. So we need to find y. So y is down here. Z here. We've got 60 degrees here, even though they didn't label it in the picture. X and X. And so in this case, we've got 5 and 7s. Now, I seem to recall, and I don't think this comes up a whole lot, but I seem to recall a long time ago learning that 5, 7, and 8 is a triangle that's got a 60 there. I actually think there's a general way to generate those, but I cannot for the life of me remember what it is. Similar to how you can generate Pythagorean triples. You can generate them all using a choice of a u and v for integers, and then I think u squared minus v squared is your a, 2uv is your b, and then u squared plus v squared is your c. And then I think you can multiply this by constants. You get all the Pythagorean triples like that. I think there's a way to get integers around a 60 in a similar fashion. I think there's a 3 somewhere in it, but I don't remember what it is. I can't imagine that the solution to this question relies on that knowledge. It's just something that pops into my head. I would suspect that this is an 8 here, though. But gosh, it was like over a decade ago that somebody mentioned this to me. And then what the heck would this one be? But if that is 8, maybe a good thing to do would be to break this up into maybe like an A and a B, or a U and a V. What will be distinct? A and a B. No, A and B is fine. I was going to say maybe we should make it P and Q, but no real reason. No, there's no particular need for a naming convention, and it kind of continues. We're sort of looping back on the alphabet here. Anyway. So I think we got a 60 here. We have a known angle. We got a known angle over here. I think we could probably just cosine law the heck out of this. And interesting, cosine of 60 and cosine of 120 are negatives of one another. And I think this might be important later on when we do Kirk triplets. But by cosine law, a squared is, I don't know, it's probably easier if I just write the regular cosine law that I can remember. So the one that opposite the angle is the 2 beside the angle minus twice az cos 60. I don't remember what that is off the top of my head. And then we've got z squared. These equations are incredibly similar. They're almost begging to be subtracted, but I don't think that's going to help because we just need a and b right now. I forgot. So 7 squared is 5 squared. Difference of 24 there. 8 squared minus 10a, and then cosine of 60 is a half. And 7 squared is 5 squared plus b squared minus 10b negative a half. Okay, so 49 minus 25, 24 is a squared, and then minus 5a. And then we also want 24 is b squared plus 5b. Okay, so what could we do here? Let's just make quadratic equations, bring everything over this. I thought that maybe I could do some sort of fancy factoring thing in my head, but not when it's written like that, I don't think. Oh, this should be a plus. 2 numbers that multiply to 24, and I need an 8 and a 3, and the 8's got to be the negative one, because then we get the negative 5. And we also have the opposite, because now the 5 is positive. But a and b are lengths. So they're positive. So a has got to be 8, and b has got to be 3. But I didn't care what that was. I wanted y. Y is a plus b, 11. And they didn't want y, they wanted the triple. Yeah, Kirk triplet. So x, y, z, 7, 11, 5. Okay. So a lot going on in that a part. A usually just serves to introduce us to the question in these later big written style ones. But there's a lot going on here. So the cos 60 and the cos 120, I'm dwelling on them because each of these triangles is going to have the 60 and 120. And so a half and negative a half, I think that's going to cancel out with these 2's here. And the x squared appearing in both, because it's isosceles, I'm telling you, we're going to have to subtract these equations or something at some point. This is actually quite general. I didn't plug in my x's and my z's. That was sort of on accident. Anyway, maybe some of this will be useful. B, determine all other Kirk triplets with z equals 5. Okay. So I think we're really just doing the same thing over again, but x isn't 7. Okay, so I'm gonna say this on the next page. I think this might help me a whole lot. By the cosine law, the following is true for Kirk triplets. X squared is z squared plus a squared minus, and then the half and the 2 will cancel out, so it'll be az, right? Yes. And then x squared equals z squared plus b squared minus bz. That's why we got those 5's there, because z is 5. Y is equal to a plus b, and we're looking at this picture right here. 120, 60. We noted this last time, but it bears repeating. because we're going to make use of it now, subtracting these x squareds from one another. And I think this might be useful in whatever they're cooking. What are they cooking up for us in C? Determine the Kirk triplet for which for which cosine of ABC, so this guy over here, is as close to 0.99 as possible. That seems unpleasant and seems like I'm going to have to grab my calculator. Okay. So focusing on the task at hand. For B, if z is equal to 5, we get x squared is 25 plus a squared minus 5a. X squared is 25 plus b squared minus 5b. Subtract the 2, we get 0 is 0 plus a squared minus b squared. Oh, this should be a plus. These should be pluses. I was wondering, they were way too similar, these equations. And then we'll get minus 5a minus 5b. And I notice here that we've got a squared minus b squared. So keep that on the one side, and then we'll get 5. And that'll be a plus b. But this is difference of squares. And if anything, actually, I'm keeping the z in here. Keeping the z in here until I absolutely need them. Z squared. So this is still all true for all Kirk triplets. The z there, the z there. So I want to divide by a plus b. This will never be 0. So a minus b has got to be equal to z. That's pretty nifty. Does that help us? So in this case, a minus b has got to be equal to 5. And knowing that this is true, I might, because as I mentioned, I think I'm a little wary of this prime number thing. It's got to pop in here somewhere because we haven't used it so far. So I think getting in a statement like this, and knowing that z is prime, might help us in some way. Not quite sure yet, but just a thought. Okay. So z is a minus b. So what can I say? A is b plus z. I don't see how that's helping me right now. It's very minimal rearrangement there. Could I plug it back in up here? What would that accomplish? Well, let's try it out. Let's plug it back in. Plug back into our first equation. So we had x squared was z squared plus a squared, but now this is b plus z squared, minus z, b plus z. I'm going to get some z squareds here. Z squared plus b squared plus 2bz plus z squared minus bz plus, no, minus is another z squared. Okay, cancels out. Get a z squared, a b squared, and then a plus bz. But I already knew this. Okay. So I don't want that. That wasn't helpful. This just turned the first equation into the second equation. Geez. Okay, so rearranging and solving for A, not so helpful. Although it does tell me A has got to be the bigger one, but I kind of already knew that from the picture. What could we do? I'll tell you what, we could substitute. We could just take the A minus B and substitute into the first equation or something. So x squared is z squared, but that's A minus B squared. Plus, A squared is minus, right? It was minus z. Minus z, but that's A minus B times A. Yes. I suppose we could also plug into the second equation, too. Will that help us? I doubt it. I'm spinning my wheels a bit here. So I might say sub into our equations. So expanding those, x squared is a squared minus 2ab plus b squared plus a squared minus a squared so plus ab. And then x squared is going to be sort of the same thing, a squared minus 2ab plus b squared plus ab minus b squared. So these extra little fellas cancel out. One of those goes away with one of those goes away with one of those. So in both instances, I know that x is a squared minus ab plus b squared. So now I've got sort of x almost in terms of a and b, I've got z in terms of a and b, and I have y in terms of a and b. What can I do with this? And I know somebody out there is probably saying, well, you haven't used z is equal to 5 yet. I know, but I haven't had cause for it yet. So what do I know? I know this one. I know y is a plus b. And I know z is a minus b. Well, I'll tell you what. Y plus z is going to be 2a. So y plus z over 2. And now I realize my 2's and my z's. I'll try and use the swirly 2. That's got to be equal to a. And then y minus z over 2 is equal to b. I could plug those in here and get a relationship between x, y, and z. See if that's useful at all. Probably going to want to multiply by 4 at some point. Oh, and there's a nice difference of squares right there. And then y minus z over 2 squared. So I'm just going to say 4x squared is, and now we've got y squared plus 2yz plus z squared minus, it'll be y squared minus z squared plus y squared minus 2yz plus z squared. Let's clean a little bit of this up. 2y squareds minus a y squared, that's just going to be a y squared. The 2yz and the minus 2yz cancel each other out. Then we'll have z squared minus negative z squared plus another z squared So by keeping the z not being a 5, I do have this relationship right here. So I like this. And I'll just remind whoever's marking for me it is true for any Kirk triplet. Because I didn't actually use z equals 5 yet. Oh, what to do now? So should I plug in my 5? I think it's time. I think it's probably time. What could I do here? Well, let's put the focus on z for a moment. And this is a difference of squares. And now I think I see why z needed to be prime. This is going to limit our options for our factors here. So once again, for b, not fob. So for b, z is equal to 5, and now we've got 2x plus y, 2x minus y, is equal to 3 times 25, 75. All right, 2x plus y is the bigger factor. And they're both going to be positive, so let's see, factors of 75. We're going to be quite limited because z was prime. We're going to have, so 3 to the 1, and so it'll be 2. There's only going to be 6 factors to deal with. A 1 and 75, that's a pair. 3 and z squared, so 25, that's a pair. And then finally, just z by himself and 3z, that's a pair. And, okay, so we can get x and y's that solve for these. And the geometric considerations are done. We just need x to be greater than z, and we need everything to be an integer. I think that's what's left. So I'm going to make a chart of my 2x plus y, the bigger factor, 2x minus y, the smaller factor. I can get y by adding these two, and subtracting one from the other and dividing by 2. And then I can get x by subtracting off y from this one and dividing by 2. And I just need my x to also be greater than z. Alright, so 75 and 1, 25 and 3, 15 and 5. So big one minus small one is 74, divided by 2 is 37. 38 divided by 2, that's a 19. So 25 minus 3 is 22, and we get 11. And then 25 minus 11 is 14, divided by 2 is 7. And finally, 15 minus 5 is 10, divided by, we get a 5 there, and then 15 minus 5 is 10, divided by 2 is another 5. So yes, yes, no. They wanted the other, or they wanted all? Determine all other Kirk triplets. So the only other Kirk triplet with z equals 5 is 19, 37, and 5. Okay, and that is a wide triangle. Okay, so that does B, and we learned a lot about Kirk triplets in the process, so hopefully, I'm just hoping here, C will go a little smoother. Now, C's got a cosine, so I'm thinking maybe we'll bring back the cosine law in some fashion here. But that's what we're thinking. Okay, so determine the Kirk triplet for which the cosine of ABC is as close to 0.99 as possible. As close to 0.99 as possible. Okay. So what is cosine of ABC? So by cosine law, I think we're going to have to bring back our A and our B, even though we forgot them for a little while. So we got Z here. I think we'll have to make use of the fact that he's a prime. We had B here, we had A here. And this is the angle we want? ABC. Okay. So by cosine law, we have Z squared minus A squared minus X squared all over negative 2AX is equal to the cosine of ABC. I probably should have named these B and C instead of A and B, but okay. Yeah, so we got that all set up. So we want that to basically be 0.99. That's the idea. That's what we're shooting for. What to do? Well, I'll tell you what. We've seen this x squared and this z squared before. What was that relationship we had? We know that 4x squared minus y squared is equal to 3z squared. Okay. Does that help me simplify? I certainly don't want my a's in here if I can help it, but he may be a necessary sacrifice. But I'd like to get some sort of condition going on here. Well, what was A? Did we ever get a nice expression for A in terms of anything? In terms of not just B and... Okay, A was y plus z over 2. So I'm going to use that. So we know that. We know A is y plus z over 2. And just in case we need it, although B hasn't reared its head yet, we have y minus z over 2 is B. Okay. I just noticed Z, A, and Y I think have to form an arithmetic sequence. Nifty. I don't know if that's going to help, but something I think I just observed. Alright. So if that's the case, then cosine of ABC is z squared minus x plus z over 2 squared minus x squared all over negative 2 x plus z over 2 x, or y plus z over 2x. Well, on the plus side, this 2 cancels out, so small victories. I suppose we can get rid of this minus sign by flipping things around. X squared plus, and then we got x squared plus 2yz plus z squared all over 4 minus z squared, and then x plus, or y plus z x. Okay, let's get the 4 down on the bottom, so that'd be 4x squared plus y squared plus 2yz plus z squared minus 4z squared. All over 4x y plus z. Alright, it's not looking the nicest yet. But I'll tell you something we can do. We can get this z squared minus 4z squared and turn him into a negative 3z squared. And I know what negative 3z squared is. So, I'm going to keep going. 4x squared plus y squared minus 2yz minus 3z squared. 4x y plus z. And then negative z squared. Negative 3z squared would be y squared minus 4xy. So that would be plus y squared minus 4x squared. 4x. Did I say 4xy? Y squared minus 4x squared. Alright, so some other things are now canceling. And we can group the 2y squared together minus 2yz over 4xy plus z. Can't quite get a y. We can get a y minus z on top. The 2's will cancel out. We'll get y minus z over 2x y plus z. I'm not seeing anything particularly useful right now. It seems like it's a perfectly valid expression, and just how useful is that? It's a shame, because I was making great progress simplifying, but has this really given us anything worthwhile? I mean, certainly now we have an expression here, cos 0.99, this cosine is now expressed in terms of my x, y's, and z's. But I don't really have... Here's my x, y's, and z's, and I don't really have anything worthwhile to show for it. I want this to be close to 0.99. I mean, I guess I could say I want it to be close to 99 over 100, maybe cross multiply, but I think that's just prolonging an admission of defeat. There's just too many variables here. So I think... So what did we... If I knew a way to generate the x, y's, and z's, I think I'd be fine. And the only way I could do that was over here with I mean, we haven't really used z as prime a whole lot. We did technically use z as phi. We haven't used z as prime. So I think go back to this. And then 2x plus y. 2x minus y is 3z squared. Now, we've never actually had to use this fact yet. Z is prime. So there will only be a few factors. 1 and 3z squared, that's a nice pair. 3 and z squared, that's a good pair. And then the only other one is z and 3z. Although, admittedly, right here... No, actually, this one's always the bigger one. Because z is at least 2, right? Yeah. Okay. However, incidentally, if z is 3, we've got a duplicate, but I don't think that's really going to impact anything. Do we have any other duplicates? No. So I guess make another chart. And I guess this will get X, Y, and Z all in terms of Z. I guess we have to be rigorous, so we ask, is it bigger than Z? But so 2x plus y, 2x minus y, y and x. So we can have 3z squared and 1. I am not liking these numbers here. But divide that by 2. And then if I were to subtract this off of here. By the way, you wouldn't get an integer here if z is 2. Anyway. So then subtract that off, and x will be 3z squared plus 1 half, and those would cancel out, but then we have to divide by another 2, so it's over 4. And I have no idea if that's bigger than z. It'll probably be context dependent. Okay, moving on to the next one. Z squared and 3. This is a little nicer. Z squared minus 3 over 2. Again, if z were even, we'd not have an integer. And then we would need z squared plus 3 halves if it was just x plus y, but it's divided by another 2, so over 4. Again, no idea if that's bigger than z. I'm not going to bother to work that out right now. 3z and z. So that'd be 2z, so you get z, and then you get z. So that one's definitely a no-go. So there's really only 2. So that's interesting. For any prime, there's really only 2 Kirk triplets, maybe, possible. Some of these might not work out to be integers, like maybe the x's won't work out to be integers, because we are dividing by 4. But that's interesting. And of course, there are other situations like the x might not be bigger than z, but we do now have possible expressions for y and x, so maybe we can sub them into that one equation. I feel like this is taking a long time. Not necessarily that this is particularly hard, it just seems like it's taking a long time. And I'm not liking that aspect, because I feel like there should be a faster way to do some of this. It's taking a while. Okay. So 3z squared plus 1 over 4, 3z squared minus 1 over 2z, and 3z squared, oh no, sorry, it's just z squared, plus 3 over 4, z squared minus 3 over 2z, are the only possible triples. I'm going to add this little maybe, just because, not that there could be more, but there might be fewer, depending on z. We may not have x greater than z or integers. I'm extremely wary of this divide by 4. Okay. So now, what is it that I want to do? So I want y minus z, 2x. I could get now this whole expression in terms of z, and that's at least progress, and then maybe I could find some prime numbers that do something. Alright, well, let's get to it. 3z squared plus 1 over 4, 3z squared minus 1 over 2, and z, the cosine of the angle that we're talking about, this whole little thing, is this really the nicest expression I have to sub in? There wasn't a better one. No, there really isn't a better one. It's a shame. Unless I could very quickly get A. A is y minus b. It's z plus y over 2 is A. So do I want to... Nah, we'll leave that expression as is. Okay, so y minus z, and then it was over 2xy plus z. I think that's what it was. Yeah, 2xy plus 7. Okie dokie, well, nothing left to do but plug in. I feel like maybe there's a nicer expression. Anyways, so 3z squared minus 1 over 2, 3z squared minus 1 minus 2z over 2. 2, 3z squared plus 1 over 4, 3z squared minus 1 plus 2z over 2. Okie. I feel like, so the 2 and that 2 will cancel out, and then these 4s will cancel out. So we'll be left with something. Something that I'm sure is meaningful. 3z squared minus 1. 3z squared minus 1 minus 2z. 3z squared plus 1. 3z squared minus 1 plus 2z. There has got to be a better formula. Because I'm not seeing a bunch of stuff that's about to cancel out. So, I'm going to put a pin in this and see if maybe I can rework the formula a little better or something. So just looking at this original formula, z squared minus a squared minus x squared. We did have some stuff with a squareds, z squareds, and x squareds way, way, way back when here. And even before. Yeah, so that was true. So x squared, we could rewrite it like that, and then we'd get an az on the top maybe, and an az on the bottom. So I'm not discounting my triplets here. I don't like plugging them into this beast of a formula. It's not going well. So we have z squared plus a squared minus x squared all over 2ax, right? Z's here, the angle we want is here, x is here, a is here. So no, wrong one. Let's get this right. So it's z squared is a squared plus x squared minus 2ax blur. So z squared minus a squared minus x squared all over negative 2ax is blur. or x squared plus a squared minus z squared. Get rid of the minus sign from the get-go. Okay, so that was fine. And then we had the 60 over here. So x squared was a squared plus z squared minus az. So I'll plug that in, so we'll get a squared plus a squared. Sorry, a squared plus z squared. Plus minus az. Plus a squared minus z squared all over 2ax. So now the z squareds will cancel out, and we'll get, take out a factor of a on top, you'll get 2a minus x over 2ax. Interesting. Is that the nicest we could hope for? I don't like the a's in there. I'm going to see if can I get rid of the a's in a nice, neat, meaningful way. I'm not entirely sure that I can with this particular setup. What if instead of plugging in for the x, I rearranged and solved for the a? So we get a squared is z squared minus x squared minus az. Alright, this should be a negative. No, the a squared here, the x squared's over here. So x squared minus the z squared plus the az. So what would happen if I plugged that one in? X squared plus x squared minus z squared plus az minus another z squared all over 2ax. So I would have 2x squared minus 2z squared plus az all over 2ax. Again, not a nice formula. What are we to do? I feel like we've come so far with these equations that I can't see the proper rearrangement that I would like to make the substitution simpler. I would have abandoned this question a long time ago. These last few questions on this Euclid are really, really, really hard. At least for me today. Maybe I'm not in the right headspace. So, what, if anything, can I still use? This 4x squared minus y squared equals 3z squared. I don't think I'm going to get that in any nice places. Because we already sort of used it to make our triples. And is there any other way to write this cosine? Doesn't look like it. But surely this is not the best formula to be using. I mean, it's way too sort of ugly. I mean, nothing, when we plugged things in, nothing is about to cancel. Nothing good is going to happen here. You get 3z squared minus 1 squared, and then minus... No. So here's this minus 3z squared. We plugged that guy in. But we had an x squared of minus y squared here. Where did that minus y squared come from? Oh, that's minus 2yz. This is what I'm talking about. My z's look like 2's. There's no way I can get a quick ratio of any of these things. So my biggest problem is this x minus z and this, this y minus z and this y plus z in here. The y and the y over x actually doesn't look so bad. It's just the x, the y minus z, and the y minus y minus z over y plus z doesn't look good. It seems off. I wish that these things had canceled or something. They don't, right? Wait a minute, we had a plus here. So we should still have a plus here, and this all should have canceled out. Okay. Now we're in much better shape. I am suppressing some rage at my own self right now. Alright, so we can clear up this and this. I'm just focusing on the positives that I found my error. Okay. At least I hope that's the error. I hope there isn't more that I have done wrong, but this is a much smoother calculation to make. This is the sort of formula I was wanting to work with. Okay, so now we get 3z squared minus 1 all over 2, all over the 2 and the 4 will cancel out, so 3z squared plus 1 all over 2. The 2's will cancel out, 3z squared minus 1 over 3z squared plus 1. This is much better. This is much nicer to work with. Okay, and we want that to be as close as possible to 99 over 100. 0.99. I'll tell you what I can do. I can say 1 over 100. It's going to be 1 minus 99 over 100. And I think this will clear up the... because they differ by just a little bit. Yeah, we'll get 3z squared plus 1 over here, and then you'll just get a 2 on top. So 1 over 100, 2 over 3z squared plus 1. Aha! Okay, so what do we need? 200, 3z squared plus 1. So I need a prime z closest to 3z squared plus 1 is equal to 200. So that would be 199 is 3z squared. Roughly divide by, I'm just going to grab my calculator. Just going for it. 199 divided by 3, that's 66. Square rooting that. We're getting z should be basically 8.144. So nearest primes are 7 and, 11, but there's no way 11's going to do it. It can't be. No way. He's way too far out. But if I had 7 squared is 49 times 3, that's not working well. And then if I had 11 squared, that would be 363. These do not look like they're going to be close at all. Okay. So what was the other one? The other expression for our trip. So these are the z's that are going to get us close. The other one is z squared plus 3 over 4 and z squared minus 3 over 2. And the expression is y over 2x. So for 3z, something over 4, and then 3z minus something over 2, and then z. I can't remember what it was. Z squared plus 3 and z squared minus 3. That was close. I wonder if the 1 over 100 is going to work as well. So 1 over 100, 1 minus cos ABC. 1 minus y over 2x, right? Was 2x. Yep. Okay. But that's just going to be 2x minus y all over 2x. And then that's going to be z squared plus 3 over 2 minus z squared minus 3 over 2. And then z squared plus 3 over 2 here. The z squareds will cancel out. We'll get a 6. And the 2's will cancel out with these 2 here. 6 over z squared plus 3. Not the nicest of numbers, but hey, what are you going to do? We need about 600 is z squared plus 3. So z squared is 597. Z is... So, square root of 597. So 24.43. So the nearest primes are going to be 23 and 29. So we just need to check 7, 11, 23, 29. Which one gets us the closest, by the way? Because that's what we want. We want the nearest triple. So assuming that all these give us triples, which I think it does, knowing that the 1 was 24, 23 is probably my best bet. But for these two, what actually is the cosine? So what actually is 3z squared, 2 over 3z squared plus 1? Alright, that's the expression we want. So for 7, that's going to be 3 times 49 plus 1, and then multiplied by 2. 0.0135, that's actually kind of close-ish. So it's even not far off. 11 squared, 121, times 3 plus 1, reciprocal, times 2. Oh, he's really far off. So far 7 is in the lead. But how good of an approximation are these ones? We need 6 over z squared plus 3. 23 squared plus 3, reciprocal, times 6. We have 0.0112. It's beating out 7. And 29 squared plus 3, reciprocal, times 6. And that's too far out. So z equals 23 gets closest. 299 over 100 for cos of angle ABC. And the triple, and we have to make sure it is a triple, or the triplet for z equals 23 is, what do we need? We need z squared plus 3 over 4, z squared minus 3 over 2, and z. So 23 squared plus 3 divided by 4. Oh, good. It is an integer. I was worried about that. And then z squared minus 3 over 2. 263, and the x is bigger than 23. So there we go. That was lengthy, to say the least. But there it is, our x, our y, and our z, and it took us a while. I don't even want to look at how long this video is. There was never a moment I really felt in control of it, except back when we were just sort of looking at the cosine law equations. But, wow. Okay. So, dust off our hands. I'm going to take a break, and then it's 10, and then we're done the 2004 Euclid, and then after that I'll be doing a Gauss grade 7, and I can take it easy. So, I will see you guys in the next video for the Euclid number 10. Thanks for watching.